Today we'll talk about turning tips and tricks, questions that I have from many users, and I will start with the setup and clamping definition, how it's related, because it's related to setup, linking strategies, approach and retract point usage, also an issue that we always have questions about it. Composite tool definition, assembly of the insert with the shank, mounting, shift, and import tools and holders from website from tool manufacturers, and defining them in SolidCAM tool STL library and for future use. So let's start with setup and clamping. Setup. Many users ask me, why do we need setup? I just want to make a profile and to output the G-code. Okay, I agree, but other users want more information, and they want also, when we create the G-code for this toolpath, to know if this toolpath is in the machine limits or if the toolpath is out or reach the machine limits. Another reason is we need to mount the part in machine space for machine simulation. That's why we need here to input values for X, Y, and Z. Other reason for why we have the setup is the setup will connect for us the correct coordinate system to a specific submachine and the correct fixture to table. So the setup have many functions that it helps us to define the part and the positioning of this part in machine. Let's start with a connection between submachine and coordinate system. We define, for example, we have a machine with 2 turrets and 2 tables, and for each turret, for example, an upper turret can work on main spindle, on back spindle. On each face of the part we have a coordinate system, upper turret on main spindle and a upper turret on back spindle. The same for lower turret, the coordinate system when we work on main, and another coordinate system when we work on back spindle. We have four coordinate system with 4 submachines, which mark is connected to which submachine. The setup will do for us the connection. It can be done automatically, because in Coordinate System Manager, when you start a new part and define only the first coordinate system, mark 1 position 1, the other 3 coordinate systems are defined automatically with the information that we have from machine ID. Each submachine has a coordinate system with orientation, X, Y, Z vector, and position. So we know how to define a coordinate system related to first one. Second, third, and fourth coordinate system we know how to define related to the first one. That's one option. That it depends also in SolidCAM settings, in CAM part, auto CAM part definition, mill turn, returning, create coordinate system for each submachine. When you have this checkbox here, and the SolidCAM will generate coordinate system automatically. If not, the user should define manually. So we have the setup. We have 4 submachines, 4 coordinate system. Setup already connects between turret 1, table 1, Mach 1, position 1. turret 1 table 2, on we see here turret table 2 when the part is connected to table 2 with and is connected to coordinate system Mach 3. Now we have X, Y, and Z shifts. For now, I don't have any shift here, any value. So the coordinate system is on the face of the chuck, or chuck back spindle. I need to tell to the software where this part is positioned and mounted in machine space. -200, for example. You see now why we need now this dimension. Coordinate system for turret 1 table 2 Mach 3 is 200 millimeters from face of the table in negative direction. The same is for main spindle. Now we can see the part here in the main spindle, but we need to pull it out. So this part should be maybe 200 millimeters from the face of the chuck. It's very easy for the user to measure this distance. In mill turn and turning only Z is important, because we define the coordinate system in center of rotation. X and Y will be 0. Milling parts, we have values also for X and Y. Not always coordinate system is in center of the part or center of rotation of 4 axis, can be in a corner of the box. So that's why we have shifts for in XYZ in setup. We position the part for each submachine related to the table. Now, directly connected to the part, it's the fixture. Fixture is connected to the part, and with this dimension also we can define precise to see part, fixture, and chuck together. Let's define a fixture. New chuck standard for main spindle. But before that, let's define I didn't define the stock, because we have here several options. I think you know all of them, but very quickly I will review them. It's a cylinder option for turning and mill turn, revolve boundary, and 3D model, also STL. But those 3 that are most used. Extrude boundary box and other 4 milling parts. The second, we have revolve, we draw a sketch here, and 3D model. Now I have here, for the first example, the stock as 3D model, and also the fixture as 3D. Stock, we talk about stock. Stock as 3D. Just click on the body, generate envelope. Okay, we have the envelope generated. Stock envelope, the blue. Now we are going to set up, and we define the fixture. I will select for the first time 3D. Fixture for main spindle. And sub. The same 3D model option. Yes, we have it. Now, why did I unhide and also the 3D models to select them and also to measure? Because I want this face of the jaw to be connected to main spindle. I want this face of the back spindle fixture to be connected to face of back spindle. Now, I just need to measure the correct values from face, because on this face we have the coordinate system, to this face we have 168 in the 165.3, for example, 165.3, and for the sub spindle from here to this face in Z161 minus. Let's check. Fixture is connected in the correct place, and for sub spindle also connected to the sub spindle. Now I will hide them, those bodies. Let's go here and hide them. Setup. Now, another question that I get from many users, they ask why I should define the place where I catch the part with jaws on back spindle, because I don't know where I will catch it. Later, after I work here, I will come with MCO and close the jaws and catch the part. Why to define it now? Because I want to catch it in any point I want. I don't want to define from start. Said, okay, you can do it. But for users that they don't use any machine control operation, they just take the part and put it on back spindle and start working on back spindle, what's happened? We need to place to position the part in the correct place. So we need the information also in these situations. Maybe you start working directly on sub spindle, or between working on main and working on sub spindle, you don't use any machine control. You manually take the part and put it on back spindle. So the software don't know where to position the part. This is the reason that we define here position of the part with fixture on main and also on back. Let's make a quick machine control operation. Just a simple movement of upper turret to see if we position, if the part is in the correct place. Machine simulation. Yeah, we can see here the part is, because I start in turret 1 table 1, submachine with Mach 1 position 1, and the part is in the correct place. But I can start this job in other submachine, turret 1 on table 2. Automatically the coordinate system is changed because of the setup. There we have the connection. Save and simulate. Now we will see the part directly connected to subspindle, and that is the way that many users there work. Machine simulation, I forgot to click. You want to start on subspindle? You can start on subspindle, no problem. We just need the information. Where do we want to catch this part? That's all. Now, if I'm using MCO, I will continue to have the information from MCO. I will ignore the setup. For example, let's go back to turret 1 position 1, turret delete. I will come with table 2, movement, let's see, in this way, yeah. With mouse wheel I move the back spindle, and in the setup we define that the fixture will catch the part here. But in MCO I do something else. I catch the part here. And part move, go to reference, simulation. Let's hide the stock. So you see the subspindle with the jaws, they will come to the position that I define in MCO. Now we ignore the setup because we use MCO. And I can work now with the part catched in this position that I define in MCO. When I use MCO, we take information from MCO. If we don't use MCO, we take information from setup. So both ways are legal and you can use them either. There are no limitations. Now, the explanation was why we need this to define in setup. It's for situations that we don't use MCO. Okay, so clamping fixture connected to table 1, a coordinate system connected to submachine, shift, where is my coordinate system from submachine? All this I think is clear now and very easy to use. Now let's start, and I will delete this example. I want to talk a little bit before the tools and importing and STL and all this. I want to talk about turning operation, linking, approach and retract point. We have several options here, and let's see how we need to use them and when. A pretty common example, but for this I will need to define another fixture and another stock. I delete the sketch. Stock I will define in standard cylinder. Okay, I select it. Yeah, takes a little bit time. Okay, the cylinder is built. Now I add some material on Z plus and Z minus, and also on the external diameter. Now this is my new stock, and this I can hide. Okay, so the fixture, edit. I will define the standard chuck standard fixture for main spindle. Go to the library, take a clamp that I defined before that. We have here only a few dimensions: JW, the length of fixture; JH, height; SW, length of step; SH is height of step. We can see the fixture 3D also. So I select clamp, and I just need to define where I catch the part. So click to be on focus on clamping diameter. We select the diameter on the stock. Axial position, also click to focus here, and let's say here. Generate envelope for me, very important to take measurement and to position the new Z. Also edit and chuck standard for subspindle. Again, go to library, take another one, position on the same diameter. I want to clamp on the stock, and in Z direction here. Also generate envelope. Now the new values are from this point to face 250, and from here to face 200 millimeters in negative direction. We can check. Yes, fixture is connected to main spindle and also on back spindle, correct. Now, what I want to show you is there are many cases when you want to work to do some turning, grooving operation here, and you want to catch the part with both tables. So let's clean here. We will do machine control to bring the subspindle, the table 2, and catch the part. We can zoom in. Yes, we are in the correct position, 162. And here in this position, table 2 check, clamp on, save, simulate. So we have the part in on the main spindle, and we came with subspindle and catch the part. This will be the situation. The part is clamped on both tables, and we want to do here some grooving. Now the problem with the grooving is that start of toolpath will start here. we will have a crash with the fixture. Add a grooving. And modify the geometry. Extend. We select a tool, a standard tool for now. Just shrunk, let's make it a little bit bigger, 30 millimeters. Select levels, technology, long external, rough, single, from middle outside, smooth, distance, without finish, you don't need finish. Simulate. Let's see where the tool path is starting. Oh, the tool is coming here in the safety point. Go to this point and start working. So we have here Z minus 83 millimeters. Here we should start, not here. But in link we have the approach point from where? From right safety corner. We have a corner here. Or when we work on subspindle, we have left safety corner. Now we need to change this. And I will say go in Z first, and after that you in X. So the first option, Z first, from 300 millimeters diameter on Z minus 83. I already see the value where the tool should start in previous simulation. For the retract point, I will say I don't need any movement in Z, only X. Go to 300 at the end of the job. Let's simulate now. Oh, we see the tool, maybe after tool change or after any other operation, turning operation, he will come here and go down in Z, start in X, and start working. Let's see turning simulation. And I put it on only 1 millimeter step. Go up on X300 and end of the toolpath. No any other movement. In machine simulation. Okay, we'll start from the beginning. Subspindle came and catch the part. Turret is in tool change position. Take the tool and come to 300 millimeters on diameter on X and Z correct position. Go down, start working. You can do any operation, or you want to cut the part, maybe you want to cut the part and take it to the subspindle with the same linking options. That's why we have them, to change the start and end point. Let's use another direct. I can go direct from a point, X and Y together. Only Z, only X, X first, Z first. All those combinations should give you full control on start and end of the toolpath. We have also direct from previous, X from previous, Z axis from previous, optimal from previous. What is previous is the previous operation. This tool work before another operation, so the previous operation have an endpoint. From this endpoint of previous operation, how to go to our approach point with all those options that we have here. So this is about approach and retract point, and linking. Tips and tricks. This is the issue today. So we learn about setup, why we have to define and how. We learn about link, approach and retract point. Now let's start to look at the tool table. In tool table, when we defined a new tool, we have all the options, rough, external thread, width, all those parameters that you need to change and define the tool. It's useful, still useful. We don't want to delete them. There are some spatial shaped tools that we don't have any other option today until we develop shape tool. We still use the old tool definition. And we have the new group of composite tools. External, and here we have a range of shapes, insert shapes that we found standard in catalogs of many tool manufacturers. They have more than that, I agree. All the time we add more and more, but this is a start. So the tool is we have the tool as a combination of two elements, the insert, the yellow part, and the shank, the gray part. So insert with all the parameters, diameter, thickness, radius, if it's left, right, and shank with dimensions, height, width, length, and angle. Different shank type, we have different insert mounting angle. This is for the external tool. Let's have an internal tool. Today we support cylindrical shanks with different dimensions, diameters from 5 mm up to 40 mm, and lengths. We have some parameters that can be changed on any tool. M, that means the distance of a tool origin of the insert up to center of shank, of center of rotation, and N, length of this area release. Another tool is grooving that we already see, and here we have all the parameters to define the insert, A and W, LA and H, and radius. And for shank we have a straight shank and a face shank. Another tool is internal grooving. Again, as internal turning, we have a cylindrical shank with same parameters for face grooving. This can be used also on face or on internal long grooving. This is for face and for internal grooving. Another tool, we have internal and external threading, in the same as internal and external turning. Okay. All this range of composite tools gives us a better way to define in a very short time a tool when is a standard tool. But when we have spatial tool, what we can do, for example, I want to make a grooving on the face. Now, the shank to make a grooving on face is different. I don't have any option to define a shank to fit here to this shape. So if I will define a job, no, let's delete only these examples, hide, add turning, grooving on face. I will select this and this line, modify extend to the stock, and select the standard tool. Let's see what's happened. I already have this tool. Let's use it. It's on B-axis turret, so I can change the angle, use this angle, levels, face, single, middle outside, 3 millimeters. No finish. Seems to be okay. Everything is okay in this simulation. No problem. But in the real world, on the machine, on the real part, let's go to Solid Verify. The first move is crash. The shank is crashing in the material, in the stock. We need here to use a spatial shank, rounded shank, to fit to this diameter. We don't have this option today, but we can go and import a tool to do this. So first of all, I have an example of a shank. Let's see here, face groove, yes. This is the shank, okay. Topology, we use insert only. I don't need the gray part, the shank, because now I have a tool that I draw, or I can download from tool manufacturer site. So in this way, with this kind of rounded chunk, I can make a grooving on the face. Let's see what the manufacturer have to give us. We look here on the website of ISCAR, and we have here the different options. We have to select the spatial tool, the correct tool for our operation, what diameter we have of a groove on the face of our part. But we have many options. I will go to take this solution, and I want a deep one, a very deep one. Let's see, we have L1, T maximum, 40 millimeters here. This tool have a 40 millimeters deep you can do, and the insert is 4. The width of the insert is 4. And here we have 3 millimeters. Let's take this. We have a 3D model as STP files, light and detailed. Now this is only the tool, but this tool must be mounted on other device, on a cylindrical device, and this device to the holder into the spindle. So this is intermediary device that we need also to add, and for example, this is the holder. I select here a config. You can select a BT, an HSK, or any other. For each one of them, the manufacturer will give us an STP, the 3D model. I download all models for now, and I have them saved. First of all, save. I have them here. I have the tool. Let's make a check import diagnostics, attempt to heal. Now tool is okay. And we have two bodies, import 1, import 3. I want only one body, so I will combine them. Now I have only one body. And remove. Okay, save. I saved as a SolidWorks part. The next is, I think, let's see what number have this device. 280.1628. 200, this is the one. Open also and save. And the last one, not this, the last one is the holder. Config with 3 parts in SolidWorks. I will create an assembly. Cancel. Save. Create an assembly. And bring them here. The holder and this intermediary part and the tool. I want to create the tool for the upper turret. So this is my the position with X up and Z in right direction. This way is the view of the user. Float and start rotating the model parallel to Z. It's also parallel to X, excuse me. And this part also rotated to me. Okay. Now let's start to make some mates. Concentric with this. And tool concentric to this. Now tool is inside up to this surface, and this surface, okay, this surface coincident with this surface. Now what else I need to do? The origin will be concentric with the tool, and right plane coincident this surface. Top plane of assembly with top plane of this part, and also top plane of assembly with top plane of tool. All parts are fixed. This is not fixed. Okay. Also top plane with top. Now it's fixed. I will save this assembly. Save as deep groove tool in downloads and export to STL. save as STL. We need just to make sure that in options we have fine, binary, unit, depend how you work in inch or millimeters. Do not translate STL output to data positive space. And when we have an assembly and we want all bodies in one single file, put the checkbox here. Save all components of an assembly in a single file. Okay, deep groove tool STL in downloads. Thank you very much. Now I need just to, no, I don't need to do anything, just to close. It was a very fast assembly. I think it takes only 5 minutes. In SolidCAM now we are going to library or STL. I have here a lot of STLs for milling and for turning. I will add a new turning from downloads. Holder mounting point, the red point. You can see the red point is here now, is where this tool, this STL body, will be connected to the station, to the turret. So the red point will define with this point there will be connected to the turret. If the export is not with the coordinate system, when you do export is not in the correct place, maybe you have the coordinate system here and you want to mount the tool with the center, so you just shift in the red dot. Now is in correct place, so X, Y, Z will be 0. Tool mounting point. In this blue point, the tool will be mounted here. We are going to X minus, I think, 170, minus 170, and Z 0. But I want shaded to mount the insert external. I can leave this here. I will make the shift in the insert, no problem. So I put here in the middle of STL body. Okay, we'll save this new body in STL holders table. In 2014 we do some change. We develop folders that this library can be will be more easy to handle. And now in our tool table I will add a new grooving tool. Go and search for my new STL, advance, 0 shift, 0 shift. The tool should be mounted in the blue point. Let's go back to topology. This is a 3mm STL, and here I will define A 3.5 and W 3mm, radius 0.1, thickness 0.1, insert only, just need to reverse the tool, now insert only, and to make this shift from the middle. I have 3.5 on A, I will move it 1.75 in Z to put the insert in the middle. Now I have the tool with insert only, and this way I can do a real simulation and a real collision check on the part. Okay, now in the job, tool, select the new tool, and I want to work from the face, width, and I need to reverse with the rounded part external. I reversed, yes. Save and calculate, simulation, let's see, solid verify. And I don't trust very much the solid verify. We still have some bugs here. Machine simulation is more precise. Here I can see anything. The tool, the stock, the part. Very quickly. So this is the way that we should define a tool, a spatial tool for this kind of problems, grooving on face, or if you have any internal groove with a small tool. First of all, you need to search for the proper tool to work, and after this to define in SolidCAM. We can import any shape with this STL option, and in this way you can see a very precise verification. But for the user that they want to make a very fast G-code and to send the program to the machine very fast, no problem. Don't download anything, just use insert only. Insert only with no holder. You didn't download, don't have time, you want a very quick operation. You work only with the insert, and you can have the tool pass, no problem. Turning, this option is also, it's also exists here. Use only the insert. So this is the way that we define tools. We talk about, let's see, I'm looking on my list if I talk about everything that I plan now. And yes, insert, shank, mounting, import from catalogs, link strategy, clamp definition, setup. I think, yes, I cover all the issues that I plan to do it today. Thank you very much, and see you in the next webinars.
Okay, Florine, thank you very much for this presentation. Thank you everyone who joined us today. I see there are no questions. So we will see you next week at the same time, and have a nice rest of the week. That's it. Goodbye.